Hello everyone. So, today we will discretize unsteady convection diffusion equation using finite volume method. So, in last lecture we discretized steady convection diffusion equation using finite volume method. Same procedure we will use here, only we need to integrate the governing equation over time as well. So, first let us write the two dimensional convection diffusion equation. So, 2D unsteady convection diffusion equation. So, in two dimension you can write in conservative form del rho phi by del t plus del rho u phi by del x plus del rho v phi by del y is equal to del of del x gamma del phi by del x plus del of del y gamma del phi by del y plus s. Here the gamma is diffusion coefficient and we have written this convection diffusion equation for any general variable phi, and s is the source term and rho is fluid density. So, in vector form if you write, then this equation you will get like divergence of rho u phi is equal to divergence of gamma grad phi plus s. So, where u is the velocity vector and this is known. So, it is linear equation because u is known. So, u I u plus v j, where you have in Cartesian coordinate, if this is your x and this is your y direction, then velocity u is in x direction and v in y direction, and I is the unit vector in x direction and j is the unit vector in y direction, and grad is del of del x I plus del of del y j. So, this governing equation now we will integrate over the main cell P. So, you can see this is your main cell. Okay. So, in this main cell P we will integrate, and these are the phase centers, okay, E, small n, small w and small s, and these are the neighbors. So, our variables are available, the value of the variable is available only at this node, okay, capital P, capital E, capital W, capital N and capital S, but we need to interpolate the value if required at the phase center. So, let us introduce the flux vector. So, your flux vector will be j, okay. So, we can write rho u phi minus gamma grad phi. Okay. So, this flux vector now is having two components, one is your convection term, one is diffusion term. Okay. So, j is like j c convection term plus j d, okay, where j c is your rho u phi and j d is your minus gamma grad phi. Okay. So, this flux vector if you put it here, then what will be the governing equation? Equation will be del rho phi by del t plus divergence of j is equal to s. Okay. So, first term represents the temporal term and the second term obviously flux. Okay. We have two fluxes, one is convection flux and diffusion flux, and right hand side term is your source term. So, in last class already we have discretized excluding the temporal term. Okay. So, now let us integrate this equation over the control volume and over the time. So, let us write here del rho t by del t. Okay. Now, you integrate over time t n to t n plus 1, okay, where delta t is your time step, okay, t n plus 1 minus t n. So, and integral volume. So, this is your in this main cell P we are integrating it. So, this is the main cell, okay. This is the main cell. So, here we are integrating dV dt. Okay. The second term similarly you can write T n to T n plus 1 volume integral, and you have divergence of J dV dt, and in the right hand side again the source term you integrate T n plus 1 volume integral S dV dt. Okay. So, first let us see the temporal term. So, this temporal term if you integrate the this term over this control volume, okay. So, what you will get? So, if volume is not changing, okay, with time, so non deforming control volume if you assume, then you will get del of del t rho phi, okay, this volume integral dV you can write del of del t volume integral, okay, rho phi dV, and this you can write as del rho phi p. So, you are now taking, so you are averaging it out, okay, over the control volume. So, you are taking the value of phi at the cell center P. So, this is your del rho phi p by del t and the volume of the cell P. So, this now you can write d of dt rho phi p delta B. Okay. So, now this we need to integrate over the time. So, if you write it, so you will get T n to T n plus 1, okay. So, you will get d of rho phi p, okay, and that delta B is not changing with time. So, you can write delta V. So, this is your integral, first integral. So, this dt and there is a dt. So, this will get, okay, or you can write dt. So, obviously, integral will give just rho phi p delta B from T n to T n plus 1 plus, okay. Now, the second term. So, T n to T n plus 1, okay. So, now you can see the volume integral, okay. Volume integral of this flux term you can convert it into surface integral using Gauss divergence theorem, and after making the assumption that J varies linearly and the average value of J lies at the phase center. So, that if you make the assumptions, then you can write the flux term as summation of over the phases J f dot S f over all the phases, okay, and dt. Okay. So, this is the second term, and similarly the last term also. So, you are taking T n to T n plus 1 and you are now averaging over the cell, okay, and the cell value you are taking at the cell center. So, this is your S bar, okay, at the cell center P you are taking, and delta V and dt. Okay. So, now you have to integrate over the time, but we will take some at some time tau and we will take some average between this tau Tn and Tn plus 1, because values are not available in between, right, only values are available at time Tn and Tn plus 1. So, this will write as, so this you will get rho delta V phi p n plus 1 minus phi p n, okay. And this term you will get plus, we are taking J f dot S f, okay, at some time level tau, which is in between T n and T n plus 1, and the last term also S bar at the cell center P S P. So, S bar delta B at time level tau delta t, okay. Here delta t will be there because you are integrating over this. So, this is, there will be delta t. Okay. So, now you integrate, now you divide both sides by delta t. So, what you will get, rho delta V by delta t phi p n plus 1 minus phi p n plus summation of J f dot S f at tau is equal to S bar delta B at tau. Okay. So, now this value of fluxes at time tau will take as summation of J f dot S f, okay, at time level tau will take as summation of J f dot S f with a factor f t at level n plus 1 and 1 minus f t J f dot S f at time level n. Okay. So, f t lies between 0 and 1. Okay. So, if f t is 0, what will be this scheme? So, only at any time level you will get, so you will get explicit scheme. Similarly, the source term S bar delta V at tau you will take as f t S bar, okay, at n plus 1 delta V plus 1 minus f t S bar n delta V. Now, let us write the flux terms. So, already these flux terms using central difference convection scheme, you have discretized it in last class. So, let us write down here. Okay. So, use central difference convection scheme. Okay. So, for that, now what is J? J is rho u phi minus gamma grad phi, okay. And now you find J f dot S f, okay. J f dot S f if you find, then you can write J e dot A c plus J w dot S w plus J n dot S n plus J s dot S s. Okay. So, all the phases, 4 phases. So, this now you find. So, what is AC? AC is your AEI. So, what you will get? So, JE dot AC. So, JE dot AC now you are going to get using central difference. So, phi E you will take, phi E you will take average of phi E plus phi P divided by 2, okay, because at this east face you are finding. So, using uniform grid phi E plus phi P divided by 2. So, that if you put, so then you will get rho, so you will get A p, okay, by 2 phi e plus phi p, this is your convection term, and the diffusion term you know you will get minus d e phi e minus phi p. Okay. What is Fe? So, Fe we have written as rho u e a e, okay, and d e is your gamma e a e by delta x e, okay, and a e is your delta y, okay, in this two dimensional case. So, now similarly you write j w dot s w and other terms. So, if you see j w dot s w, so we will write minus f w by 2. So, it will be average between this w. So, if you take the central difference convection scheme, it will be phi p plus phi w divided by 2. So, it will be phi p plus phi w divided by 2 plus the diffusion term will be d w phi p minus phi w, okay, where f w we are defining as rho u w a w, okay, and d w is gamma w a w delta x w. Similarly, now you write for other two terms. So, you will get j n dot s n if you write. So, it will be f n by 2. So, phi n plus phi p minus d n phi n minus phi p, and for the last term you will get f s by 2 phi p plus phi s minus, sorry, it is plus d s phi p minus phi s. Okay. So, now rearrange it and write as, so here f n is rho u n a n and d n is gamma n a n by delta y n, okay, and a n is in this case delta x, and f s is rho u s a s and d s is gamma s a s by delta y s. And what is u s, u n, u w, u e? You will take central difference. Okay. So, u e you can calculate as u e plus u p divided by 2. Okay. Here also we are using central difference. Okay. So, now if you rearrange it, okay, you are going to get, so all the p terms you take. Okay. So, for p terms you see what are the p terms. So, this is your p, 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 p and p. Okay. So, if you take all the p terms together, then you see it is will be minus minus plus. So, it will be d e phi p. So, first we will write d e, okay, plus f e by 2. So, for this phi p, this is f e by 2. So, this is f e by 2. Okay. So, this is one coefficient. Then for this you will get d w minus f w by 2, d w minus f w by 2. Then for this north you will get d n plus f n by 2. Okay. Then you will get plus d s minus f s by 2. Okay. So, this is the coefficient of phi p. Now, for the neighbor terms you can see, so this is your east, this is your east. So, you can write it. Okay. So, we will write taking that minus, okay. So, we will get d e. So, this is your minus. So, we have taken outside. So, d e and here minus f e by 2. Okay, because it is plus. So, minus I have taken outside. So, it is minus f e by 2 phi e plus d w plus f w by 2 phi w. Similarly, the other terms d n minus f n by 2 phi n, all are neighbor terms, okay, and ds plus fs by 2 phi s. Okay. So, now if you define the coefficients as A e is equal to d e minus f e by 2, A w as d w plus f w by 2, A n as d n minus f n by 2, and A s as d s plus f s by 2. Okay. So, you can see this term you can write as A e, okay. This is your A w, okay. This is your A n, and this is your A s. Okay. So, and this term, the first term, okay, this you simplify. So, if you write first term this one, so you can write as, you see, d plus f e by 2, I will write as A e. Okay. So, if you write A e, so what is A e? So, d minus f e by 2. So, I have subtracted minus f e by 2. So, again you add plus f e by 2. So, let me write here. So, I have d e plus f e by 2. Okay. Now, I want to write in terms of coefficient A e, but A e is d e minus f e by 2. So, if you write d e minus f e by 2, I am subtracting 1 f e by 2, you add another f e by 2. Okay. So, then there will be no change, and 1 f e by 2 is already there. So, now this d by f e by 2 is A e, and f e by 2 plus f e by 2, it will be f e. Okay. And similarly, d w minus f w by 2, what you can do, the second term you can write d w plus f w by 2, and you subtract 1 f w by 2, there will be no change, then minus f w by 2. So, this you can write as A w minus f w, okay, because this minus f e by 2 and minus f e by 2 will be minus f w. Similarly, for other coefficients you can show, and finally, we can write the first term as A e plus A w plus A n plus A s minus plus f e minus f w plus f n minus f s. So, this is the coefficient of phi p, okay. And we have A e, okay, and we have minus A e phi e plus A w phi w plus A n phi n plus A s phi s. Okay. So, now this we can write as, so you can see this is your, so this A e plus A w plus A n plus A s, we can write summation of A n b, because all neighbor coefficient summation, okay. And this f e minus f w plus f n minus f s, okay. So, this we can write as summation of f f. Okay. What does it mean by summation of f f? So, summation of f f is net outflux. Okay. So, this is your mass flux. So, obviously, it satisfies the continuity. So, in the beginning of the solution it may be non-zero, but at the convergence summation of f f will be tend to 0, because it will satisfy the continuity equation. So, this we have written, then this is your phi p, okay, and this you can write as minus summation of A n b phi n b. Okay. So, now these fluxes, now you substitute in this expression. So, we will substitute in this expression this jf dot sf, okay, with the term n plus 1 and n. So, we have rho delta v by delta t phi p n plus 1 minus phi p n. Okay. Then we have summation of jf dot sf, okay, with a factor ft and at level n plus 1, and we have 1 minus ft summation of jf dot sf, okay, at level n, and we have the source term ft s bar n plus 1 delta v plus 1 minus ft s bar n delta v. Okay. So, now we have already written this term. Okay. So, summation of jf sf we have written in this form. So, this let us substitute it there. So, summation of jf dot sf we have written as summation of a n b plus summation of f f, okay, phi p plus summation of a n b phi n b. Okay, here it is minus. Okay. So, now if you put it there, so you are going to get rho delta b by delta t phi p n plus 1 minus phi p n, okay, plus f t. Now, this whole term at n plus 1 level. So, you have summation of a n b plus summation of f f phi p minus summation of a n b phi n b at level n plus 1, and we have 1 minus f t, again we have summation of a n b plus summation of f f phi p minus summation of a n b phi n b at n. So, n let us write in this way, n plus 1, this is your n plus 1, and this is your n, and this is your n, and let us write this source term plus b, okay, where b contains the source term. So, now you take the phi p n plus 1 these terms in the left hand side and all other terms you take in the right hand side. So, let us rearrange this equation. So, phi p n plus 1 you see phi p n plus 1 here we have and phi p n plus 1 here we have. Okay. So, this you take in the left hand side. So, you can see if you put a p 0 is equal to rho delta v by delta t, okay, a p naught, okay, if you write rho delta v by delta t. So, now you see a p naught this phi p n plus 1, okay. So, this will take here. So, it will be f t, okay. So, f t into this. So, plus f t summation of a n b plus summation of f f, okay, into phi p n plus 1. Okay. So, this is whole bracket. Okay. So, this is the coefficient of phi p n plus 1. Now, you take the neighbor term in the right hand side. So, this is your neighbor term n plus 1 and this is at n plus 1. So, this you take in the right hand side. So, equal to, so you can write summation of a n b. So, you see this is minus, okay, and minus f t, and here also minus 1 minus f t. So, let us take in the right hand side. So, it will become plus. So, it will be f t summation of, summation already we have taken. So, f t phi n b n plus 1, okay, and this term if you take. So, it will be plus 1 minus f t, okay. So, this we are taking in the right hand side. So, it will be phi n b at n. Okay. And what is left? So, phi p at time level n. So, this is your phi p at time level n and this is your phi p time level n. So, that you take in the right hand side, sorry, here it will be equal to b. So, it is equal to, you please correct it. So, it is will be equal to and this is equal to b. Okay. So, this whole term we are considering as the source term b and that will be in the right hand side. So, equal to will be here and here also will be equal to b. So, please correct it. So, now you write all this phi p term at time level n. So, you can see this will come negative. So, right hand side plus. So, it will be a p naught. So, plus a p naught. Okay. Then we have this, if you take in the right hand side. So, it will be minus 1 minus f t. Okay. Then we have summation of a n b plus summation of f f. Okay. Summation of f f. So, phi p n and plus b. Okay. So, the coefficient of phi p is the diagonal coefficient that we can represent as a p. So, you can write a p as a p naught plus f t summation of a n b plus summation of f f. Okay. So, this is your diagonal coefficient and a p naught is your rho delta v by delta t. Okay. And we have b. So, b is f t s bar n plus 1 delta v plus 1 minus f t s bar n delta v. Okay. So, this is the final discretized equation for this unsteady convection diffusion equation and we have written in terms of the coefficient. So, diagonal coefficient is a p and phi p n plus 1, obviously it represents the value at the cell center and that is your I j, right. So, p phi p, obviously it is phi I j and similarly you can see that east will be I plus 1 j, I minus 1 j and this north will be I j plus 1 and south will be I j minus 1. Now, if you consider the special cases. So, f t if it is 0 then it will become explicit. So, you can see if f t is 0, special case if you consider f t is 0 then it will become explicit scheme. Okay. And obviously, you will get f t is 0. So, you will get a p naught phi p n plus 1. Okay. And in the right hand side you will get summation of a n b phi n b at n all the faces. Okay. F t is 0. So, you will get a p naught. Okay, minus summation of a n b plus summation of f f at phi p n plus b. So, you can see here right hand side all are at nth time level. Okay. So, all are known from the previous time level and left hand side you have phi p n plus 1. Okay. So, you are actually calculating at present time level phi p n plus 1. So, one unknown and right hand side are known. So, obviously, it is explicit scheme and it is order of accuracy is first order and this you can see if f t is equal to 1. So, you will get implicit scheme. So, in this special case it will become a p naught. So, a p will be a p naught plus summation of a n b plus summation of f f. Okay. So, you will get A p phi p n plus 1 is equal to, and in this case if you represent A p, so it will be A p is equal to A p naught only, and B will be only S bar n delta V. Okay. And here it will be S bar n plus 1 delta V. So, A p naught phi p n plus 1, and right hand side you will get summation of A n b all the neighbors, okay, phi n b at n plus 1. Then next term you will get plus A p naught phi p n, okay, and plus B. So, B only S bar n plus 1 delta B, and you can see that right hand side all the neighbor terms at n plus 1, left hand side it is n plus 1, then you will get more than one unknown. So, it is implicit scheme and it is also first order accurate, and f t is equal to half if you put, then you will get Crank-Nicolson. Okay. So, in that case you will get A p is equal to A p naught half summation of A n b plus summation of f f, okay, and B you will get half of S bar n plus S bar n plus 1 into delta V, and the equation you will be getting A p phi p n plus 1, okay. Then you will get half summation of A n b phi n b n plus 1 plus phi n b n, okay. So, then you will get A p naught minus half summation of A n b plus summation of f f phi p at n, and plus the source term. Okay. So, today we considered two dimensional unsteady convection diffusion equation, and we integrated this equation over the main cell P and over the time. Then we have written the discretized form in general way, and we have considered few special cases where f t is equal to 0 it is explicit, f t is equal to 1 it is implicit, and f t is equal to half it is Crank-Nicolson, and obviously Crank-Nicolson is second order time accurate. While discretizing these equations, we considered central difference convection scheme, but you can extend it to first order upwind scheme. Okay. So, this may be your homework. So, you just consider first order upwind scheme and discretize this equation and find the coefficients. Thank you.